Okay, so homework 2 is back for those of you who turned it in.
Oh, I have it. Oh, crap. I forgot to turn it in, but I have it. Sorry. Go ahead.
Don't get all discombobulated. You can give it to me after, since I appreciate that, I think. So, okay. Now, it's fine for the rest of you, because I think I have like 3 or 4 outstanding. So, all right. Now, where are my notes? Here are my notes. Okay, I want to make sure these are the correct notes. Yes. Okay. All right. Admittedly, I maybe it's an overreaction, but I don't care. I felt like I made a mess of things on Wednesday, but as you guys well know, it was not my day or week. And also the fact that there was one example that I meant to cover, but I did not get to at all. And then the other example, which I did present, was done in such a rush. And then stuff before that, in a complete mess of, at least internally. And actually, I did watch the video. I don't normally watch myself, but I did watch the video of that part, and it's like, so the first part I did on Wednesday, the derivation of a formula, that part was okay. So it's the rest of it that's, I'll make sure that is cemented. So that's why homework, chapter 4 homework is not due until after spring break. Okay. So a solution formula that was derived at the start of last time, we're going to pick up so I'll write out the problem. You see t minus t squared uxx is big F of xt on the entire real number line. And t greater than 0. And then the usual initial conditions. Okay. So the solution formula is this. We have the familiar Hilbert solution formula for the homogeneous wave equation. So that's the first couple. That's everything I've written up to this point through this integral. Okay, so this is solution to the homogeneous part. That's under my army card already. Okay. Well, I guess I have been writing on the board today a lot more than usual. Okay, so that's a homogeneous equation with the same initial conditions. And then the non-homogeneous part is where we integrate the source term, and I'll label this. Okay. Over the characteristic triangle. So that's the domain of integration here. That has the vertices xt at the top, x minus ct 0 at the bottom, and x plus ct 0 also at the bottom. And I've normally abbreviated the characteristic triangle is just delta. So we're integrating big F of squiggly tau over that characteristic triangle. So it's only in this term that the non-homogeneousness, if that's a word, of the PDE comes into play. Okay, now at the beginning of class on Wednesday, this was derived using Green's theorem. So all of that is fine. So anything in your notes past that point, once we arrived at the solution formula, feel free to just cross it out. So, and not so much because it was wrong, because actually anything actually made it into your notes probably was perfectly correct. But, well, actually, almost everything. But I want to have something clearer at least. Okay. More time to get that settled, and let's see.
Yeah, then we verify that it is a solution.
Yes, yes. That's where things started to go badly. Okay, so everything up to here is fine. All right. And this way I'll also have more time to do the examples, which are important for the homework. Okay.
Then we did like stuff related to homework, like is FG or odd even functions, we talked about that. And then you gave an example of, UTT minus 9UX. Those are fine.
That example I want to revisit just because I had to rush it. Yeah. Yes.
On the characteristic triangle, isn't the T usually stuck here?
I think when I first derived it, I called it x naught t naught.
Mm-hmm.
It doesn't really matter. You're just expressing a solution at some point. Yeah. I think as far as how the solution formula was expressed, I think. Oh yeah. So what I had in the notes was x naught t naught, which allowed me to use x and t as my variables of integration. But because I'm using xt out here, I need to use something different inside. But actually, this will make it more consistent with what I'm about to do. Okay. Okay. So, verification. All right. So first, for splitting. Our initial value problem. So this is what we had to begin with. So a solution to this, so U equals V plus W, where V, so U is the solution to our original problem. V satisfies the same PDE, same inhomogeneity, but with 0 initial data. Okay. And W satisfies the homogeneous wave equation with the original initial conditions that we impose on U. And the thing is, W is null. That is the original delevered solution formula.
You mean for the homogeneous?
Yeah. So that just contributes the first part of a solution formula I wrote over there. Everything except the integral over a characteristic triangle. So in other words, we just need to show that V of xt is equal to being equal to is the characteristic integral of a characteristic triangle. So, so that is a solution of this problem here. But it actually satisfies the non-homogeneous wave equation, and that it also satisfies the initial conditions being 0. Okay, and that would do it. So then we could just add that to the terms we already know we get from W, and then we get the solution that we expect to get that's written over there for U. So that would cover everything we need. And B of x0, if we just go ahead and plug in t equals 0, that's the integral from 0 to 0. But the integral from 0 to 0 of anything, once the limits are the same, that's 0. So that initial condition is satisfied. And now, for differentiation, which is where things kind of got ugly, we need to differentiate this solution b of xt with respect to t and also x. And what I referred to last time is the evil fundamental theorem of calculus. And that is that if you have an integral of some function, I'll call g, and the idea is you have an integral that depends in many ways on your variable t. So t plays a role in both limits, and it plays a role in the integrand itself. So we're integrating with respect to s, but t is playing a role of some parameter that also affects the integrand. So if you have all these different kinds of dependencies, then how do you compute the derivative of that with respect to t? Okay, and the fundamental theorem of calculus combined with the chain rule gives you that. So it starts by plugging in your limits in for your variable of integration. They get plugged in for s in this case. So you get g of b of t, and then the other t is still there. But because of a chain rule, we need this derivative. Okay, and then minus the same thing for the lower limits. Okay. And then to account for the dependence of the integrand on t, that's where we have still an integral, still the original limits, but now you take a derivative of what's inside with respect to t. But you're still integrating with respect to s. Okay, so that's what has to be used. And the thing is, because in this case, we're applying this to this double integral, so your integrand is itself an integral. And that's where things get messy, and you have to be extra careful about how you apply this. Okay. All right. And you know how it is when, especially when you're like working through a homework problem, and you're just not getting it right, and your brain just wants to do a certain thing wrong, and say, like if you ask me about it, and I tell you, no, it's not like that, it's like this, and your brain still wants to do it the wrong way. That's what happened to me in class on Wednesday. And I watched myself in the video, it's like, what are you doing? You know it's not that. What's wrong with you? So, it was painful to watch. So, Okay. I didn't want that to affect your chance of understanding all this. Okay. So, the first thing we're going to do is, we got this initial condition out of the way. We need dv dt because we need to check this initial condition too. And eventually we need vtt. So to differentiate this in respect to t, we're going to take this integral, treat it as a function of t, and with these limits, and then this inner integral, that's playing the role of our, so g of tau t, if you will. So t is your outside variable, but because the outer integrals with respect to tau, you think of it like this. And then g itself has this additional dependence on xc, just because it itself is an integral, which just makes things even worse. Okay. All right. So, how we apply this, okay, actually, before I switch boards, I want to have everything side by side, especially for people watching at home. Okay. Okay. Now, so with v of xt, the integral over this characteristic triangle. Okay. So derivative of v with respect to t, in applying this, the first thing we're going to do is we're going to take the limits, these limits, and substitute them into the integrand. So we're going to get 1 over 2c, but when we substitute the lower limit, we multiply by the derivative, but the lower limit is constant in this case, so that's going to give us 0. So we're not going to have this term at all. We're only going to have this term. And this derivative, since our upper limit is just t by itself, the derivative is 1, so we're just going to have a 1 here. So, so all we're going to have is, actually I'll write it this way using like notation commonly used for evaluating things at a certain point, especially complicated expressions. So we've got 1 over 2c just sitting there, and we're going to have this inner integral evaluated at actually just evaluated at because the outer integrals with respect to tau, we're going to set tau equal to t times this derivative dt dt, but that's just 1. And then this part we're not going to have at all because the lower limit is a constant. And then we need this integral over here that keeps the original limit 0 and t. And then we have derivative with respect to t of whatever you have inside. Okay. d tau. Okay. So we go ahead and set tau equal to t in here. That's going to give us the integral from x to x. But again, the limits are the same. The integral is 0 because basically you have a shape of 0 width. So that part worked out nicely. And then, as for this part right here, I'll make sure here this is a plus right here. So now, that same fundamental theorem of calculus, we have to apply again. So what happens is, we're going to have the integral from 0 to t, like before. That part doesn't change. It's just what's in here that's different. So what does this call for? Whatever you have for limits, your a and your b, you're going to substitute in for your variable of integration, whatever that is. In our case, what is our variable of integration though? It's c. So these limits get plugged in for c. And that is the point on Wednesday, where my brain began to give out. So what we'll have is f of this upper limit, x plus c t minus tau, times the derivative of this limit with respect to t, which gives us a c. So this is a derivative of the upper limit with respect to t. Okay. Minus same integrand with the lower limit plugged in for c. Forgot still have tau as a second variable. All that times c. Tau is a second variable still. And then a derivative times the derivative of this with respect to t, but that's minus c d tau. Okay. So now, all this can be simplified. First of all, the minus and a minus give you a plus. Also, both terms have a c, which cancels out with a c down below. So cancel, cancel, and then the minus and minus make a plus. But that c also cancels out. So now I can express this whole derivative with respect to t as 1/2 integral from 0 to t f of x plus c t minus tau tau plus f of x minus c t minus tau tau d tau. Okay. All right. From this, you can see quickly that the VDT at x0, you plug in t equals 0, is 1/2 integral from 0 to 0 of all this stuff. So that's going to be 0. So both initial conditions check out. Okay, so this is kind of a pain to apply this terrible fundamental theorem of calculus. You actually had to do it twice. First on the outer integral and then later on the inner integral. But this is what you get. So, any questions about this monstrosity?
Yeah, one small question.
Yeah.
when you got dt over dt, I understand that a prime of t is 0, and that goes away.
Right.
About b prime of t will just be 1. How about the gb of t comma t? Like, what role does that play?
Oh, so here, yes, so what happened is, so you plug in t for your variable of integration, which, so in this case, for the outer integral, your variable integration is tau.
Right.
So you're plugging in your upper limit for tau.
Which is t.
Yes. But the thing is, where do you plug it in? The only place to plug it in is here, in the limits. And that's why I have this vertical bar notation. So this indicates that this whole monstrosity, you have to plug in t for tau. But what happens when you do that? The only place you plug it in,
is in the limits and makes it x to x, and that goes to 0.
right.
But then
Actually, here also. Not that it matters, but
right. Okay, that goes to 0, and then you have like times dt over dt. How did you sort of?
that came from this, b prime of t.
Okay.
Yeah. So all of this
Right.
matches with all of that.
Goes to 0.
Yeah.
So, yeah.
Okay. Any other questions? Okay. All right. How much time have I gobbled up on that? Okay. A little bit worse. Okay. All right. That's dVdt. Well, just to check out, and then in order to continue, this has to be differentiated again with respect to t. And okay, I'm going to try to complete that on this board. At least this is a okay. Well, actually, that is almost as nasty an application of the same fundamental theorem of calculus. So actually, there's no way on earth I'm going to fit it on this board, am I? Well, yeah. Oh, this is problematic recording-wise. So no, I'm going to have to go back to this board. But I'm going to leave this fundamental theorem of calculus up, just so I can refer to it. Because it's a pain when you have to use the whole thing. No, not just plugging in both limits, using a chain rule and all that, but also dealing with this part. And that's what we have to do, we're about to have to do to compute VTT. Okay. The derivatives with respect to x are a lot less interesting, thankfully. Okay. So VTT is a derivative with respect to t of this integrand that has t as a limit. Oh, there's 1/2 in here. Okay. So what happens is, first you plug in, so differentiation cancels out the integral, and you plug in t for tau. Here, everywhere you see a tau. So 4 places. So what we get is 1/2. So from the first term, you get, well, this goes away. So you just have xt. And then from this term, you get again f of xt. And then you have the integral again, from 0 to t. And you need to take the derivative of this whole expression with respect to t. Okay. Now the thing is, you have to look, where's the t dependence? It's only here in the first argument to capital F. The second argument is this tau, which has nothing to do with t. All right, so the first two terms simplify to this big F of xt. So you can forget about that. So, in taking a derivative of this whole thing with respect to t, we have to use a chain rule. So we're going to get partial of f with respect to x, and then, because x is the first variable for big F, times the derivative of x plus or minus c t minus tau with respect to t. So that's actually what the chain rule is going to give us to get the whole dependence of the integrand with respect to t. I need a little more vertical space because of what I just wrote. So that's going to give us 1/2 integral from 0 to t fx of this whole expression times the derivative of this with respect to t, but that gives us a c, and then df dx again times the derivative of this with respect to t also, that gives us a minus c d tau. So now what I can do is, I have a c throughout, so I can just put it here. As long as I remember to put a minus in the middle. And that takes care of VTT. Okay. So any questions about that?
After that, you're going to have like a t minus t comma tau. Right?
Oh, yeah, there's that. All right, I keep forgetting that. Okay. All right, so now I have all the derivatives I need.
Wait, what did you just change?
Oh, I forgot the comma tau.
Oh.
I forgot it here, remembered it here. Okay. Now, we need to go back to the original expression for v and take derivatives with respect to x, but that's not quite as nasty as what we had before. Okay. So dv dx is partial with respect to x of this whole thing. Okay. So what happens is, when you're differentiating this with respect to x, you look at the outer integral. Well, none of the limits in the outer integral depend on x. So these first two terms from a fundamental theorem of calculus, which I still have written over here. Okay. Here, these terms right here will not apply. It's only this one that's going to apply, because that's where you have an actual, you need a dependence on x, because you're differentiating with respect to x. Okay, so that simplifies our work a little bit. Okay. So it gets 1 over 2c, and then integral from 0 to t, and then you can differentiate this inner integral with respect to x, and in that case, what that means is you're going to plug in these limits in here. And then the derivatives of these limits with respect to x is just 1. Also, there's no x dependence in the integrand, so you don't have to think about that. So this works out much more nicely than before. So what you get is 1 over 2c, integral from 0 to t, and then you just plug in these limits for c. So you get f of x plus c, t minus tau, tau, minus big F of x minus c, t minus tau, tau, d tau. Okay. And then for Vxx, it's similar to what happened in VTT. You're only going to work in here. You're just going to differentiate this with respect to x. So Vxx is 1 over 2c again, integral, so none of that changes. And then you differentiate these with respect to x, and the derivatives of these arguments with respect to x is 1. So you're not going to get those factors of c like we did before. That only happened with a t differentiation. So you just get fx, x plus c, t minus tau, tau minus fx, x minus c, t minus tau, tau, d tau. And from there, if you compare Vxx with Vtt, which I have, okay, is written here. If you put the two together, you get Vtt minus t squared Vxx is, everything cancels out, but the integrals cancel out. The only thing that doesn't cancel out is the big F of xt. So it satisfies the non-homogeneous wave equation. Okay, and I'm much more satisfied with that verification of it than the one I had on Wednesday. Okay,
So did we just like redo the crap on Wednesday?
yes.
Okay.
Well, it was a mess.
Yeah. Okay.
Okay.
I kind of feel dumb for asking that, but
That's okay.
I don't know.
Well, good. Well, besides, I told you guys I was going to do that. So, okay. Now, in the remaining time that I have, I want to talk about things that will help most directly with homework problems for this chapter.
Yeah, especially that pressure problem, I think it's like
Which one?
the P now, like the P, where will the building survive or something like that.
Oh,
So
okay.
it's Sort of, yeah.
Oh, I think that's actually a homogeneous wave equation, isn't it?
There's another one which is not homogeneous, right?
Yeah, there's certain ones that are not homogeneous, but like, okay. Now, this is something from calculus. Fx is even if f of minus x is equal to fx. F is odd if f of minus x is equal to minus f of minus x. So there's a result about if initial conditions in big F are even, if they're all even, then the solution is even. If they're all odd, the solution is odd. If they're periodic, then the solution is periodic. And part of the proof is done in the text, and one of the homework problems is to finish it. So for
Minus
instance,
F of X.
what?
The second line you need minus.
Yes, okay. All right, yeah, so otherwise I'm saying it's 0. Although f of 0 is 0 if it's a odd function. Okay, so let's suppose that f be even. So f of minus x is equal to f of x. So if you differentiate both sides, so derivative with respect to x of f of minus x is therefore the derivative is equal to f prime of x, because I'm just differentiating both sides. But what happens when I differentiate the left side? If I actually carry that out, what am I going to get? If I go from this.
Negative f prime of x.
Almost.
F of negative x is negative 1.
Um,
Are you chain ruling
yeah,
it?
yeah, yes, f prime of minus x.
I forgot to say the prime.
Negative
But yeah,
f prime
times negative 1.
Times negative 1. Okay.
Yeah.
Negative f
I
prime
just
of
forgot to say
negative
the prime. If that's
Yeah, so in other words, f prime of minus x is equal to minus f prime of x. So what, if f is even, what does that mean about f prime? What? Yeah. So odd and even toggle from one differentiation to the next. Okay, so if f is even, what can we say about its second derivative?
Even.
It's even. So you get an idea from that why evenness in the initial data leads to evenness of a solution. And similarly for oddness, derivative of an odd function is an even function. So it all works like that. Differentiation toggles between odd and even. Okay, sine is odd, cosine is even, derivative of sine is cosine. You get the idea. Okay, actually one reason why they call it even or odd is that based on this definition, even powers of x are even, odd powers of x are odd. Sine x, Taylor series, is odd powers of x. So sine is odd. Cosine consists only of even powers of x, so you can see from that why it's an even function. Okay, let's look at periodicity. F is, say, p periodic if f of x plus p equals f of x. Okay, let's differentiate both sides of this. So on the right side, you just get f prime of x. So what's the derivative of the left side?
F prime of that. We're taking with respect to x, right?
Yeah,
Prime
That's
of
just times 1.
yeah, times 1. So if f is periodic, we can conclude that
1. Derivative is also periodic.
the derivative is also periodic. Yeah, so that's the key to doing that part. Yeah, we'll take sine and cosine. They're 2 pi periodic. The derivatives are cosine and minus sine, also 2 pi periodic. Because a periodic function can be expressed as a sum of wait. It can be expressed as sum of this form where omega is an integer. So what happens when you differentiate that? You're just going to multiply this. So if you differentiate with respect to x, you have some coefficients. So all you get is multiplied by I 2 pi over p omega times the same exponentials times the same coefficients. So you can see what these are p periodic functions. So are these. Because only the coefficients of the expansion change. So you see why periodicity survives differentiation. Okay, so that can help you with that problem. Okay. The remaining time, okay. There's one example I didn't touch at all. I want to make sure that I at least do that. Okay. So we have a non-homogeneous wave equation, UTT minus UXX. So C is 1. It's T to the 7th. And then here's our initial data. So what we can do is, like I broke down the problem before, u equals v plus w. So v satisfies non-homogeneous wave equation with 0 initial data. And w satisfies a homogeneous wave equation with the initial data of the original. Okay. Now, so what I can do is, since my right-hand side, my big F of xt, is a function of only t, instead of using a solution formula that I painstakingly derived and then proved twice,
You separate it and do it with each one, like you did the other day. You did an example like that.
yeah, that was actually worked out one way I did here, and I would a different way in the notes. But yeah, but it's the same idea, because if your right-hand side depends on only one variable, there's a shortcut. So I could I could try to find a solution. So I can let v of xt be just a function of t only, and a reason for that is that way vxx is 0. And now it's also important, though, that my initial conditions are independent of x. Otherwise, I could not do this. So I have to make sure that everything depends, and all problem data depends only on one variable. So in this case, it depends only on t.
But if you're going to use v, they are going to be x dependent.
Sorry, what?
If you're going to use v's, they're going to be equal to 0, right? So
Well, only the initial data, though. But yeah. So v of 0 is 0.
okay.
Yeah.
But that's how it's going to always work, right? Because v will always have 0 initial data.
Yes. Okay. Yeah. Sorry, I wasn't sure what you were asking, but yeah.
Oh.
Yeah. If you break it up like this, then yeah, it's moot.
Right.
But I'm just saying, like, it's something to be careful of for a general problem.
Okay.
Okay. So vxx is 0. So we're only solving a problem vtt equals t to the 7th. V is 0 and v prime of 0 are both 0. So how can we go ahead and solve that? What's a...
Just integrate twice.
Yeah. So what's vt?
7t. Oh wait, you're integrating respect to.
1/8 t to the 8th.
Yeah, you
Oh wait, I was.
do it the wrong way.
Yeah, whoops.
All right. Now you have to make sure it satisfies v prime of 0 is 0. Does it?
Yeah.
Yeah, you plug in t equals 0, you get 0. So you don't need to add a constant of integration in this case. But for other problems, you might. So you have to be careful about that. It depends on what you have here. Okay. So v is going to be what?
T to the 9th over 7t.
Yeah, t to the 9th over 72. And that satisfies v of 0 is 0. So that's all you need. So v is complete. So now you can write down the whole solution. So u of xt is the homogeneous D'Alembert's formula for this initial data, and that's just going to be 1/2 2x plus t plus sine x plus t plus 2x minus t plus sine x minus t. Okay, so that's and then for a homogeneous solution, you have an integral of g, but g is 0. So we're not going to have anything from that. So now you can just add on this, t to the 9th over 72, and that's it, you're done. Because we have in the problem already that c is equal to 1. Okay. Notice that the t terms here cancel out. So you get 2x plus 2x over 2 is just going to be 2x. And then you're going to have, here we have a sign of the sum and sign of the difference. So you can actually,
Cosine, sine, cosine.
yeah, you get, it works out to sine x cosine t from this sum and difference identities for sine. So if you were to work that out, just look up your trig identities if you don't remember them, and it all works out that way.
What'd you do at the end there? Did you plug in the ICs?
No.
What would you to get
All I
the
did was,
Yearbook to?
V's canceled.
No. Before that, like, where'd you get your Yearbook to?
Oh, from V initial conditions.
That's what I said. You plugged in the.
Oh, okay, I thought you were talking about something else.
No.
Yeah.
Okay.
Okay. Any other question?
I don't understand what she was saying, like what? What was, like,
Oh, how,
How
Where-
did he
where-
get, where did that come
where
from?
this part?
Well, that's the, yeah, and then like using the homogeneous.
Yeah, the homogeneous solution formula, yeah. Okay. Now, what's interesting is in a textbook, and therefore I use this in my notes, for the other example, the original solution formula I've been working with earlier was used. But in that case, the function big F of xt depended only on x. So there's no reason why the same tactic could not be used, just a little differently. So I'm going to go ahead and show you that for that example. So it's worked out two different ways. One way in the notes, and by the way, after Wednesday's class, as I mentioned, I think in the email, I added to the notes a little bit, just a few more steps for elaboration. Okay. So for our example, we have utt minus 9uxx is equal to e to the x minus e to the minus x, which is the same as 2 sinh x. And our initial data, ux0 is x, ut of x0 is sine x. So, so we compute v and w. So for v, we have v of xt, I'll assume, is a function of only x. So it's called v of x. So that means that we have minus 9 vxx is equal to 2 sinh x. So actually, I'm just going to move a minus 9 over to the other side. So that is an equation that we can go ahead and solve by integration. So I integrate both sides with respect to x, and I have my initial conditions. V of 0 is 0, v prime of 0 must be 0. So what do I get when I integrate sinh? Cosh. So I get minus 2/9 cosh x, but does that satisfy the initial condition for v?
Cosh of 0.
What is cosh of 0?
Is it 0? No.
No, it's not. So cosh x is e to the x plus e to the minus x over 2, and sinh x is e to the x minus e to the minus x over 2. So in fact, cosh is even and sinh is odd, just like cosine and sine are. So what is cosh of 0?
1 plus 1. Oh, that's
It's
1.
Wait,
1.
Anything to the 0.
Could
1
be-
minus 1 is 0.
Sinh of 0 is 0.
Yeah, that's 1 plus
Cosh,
1 over
that's a
2.
plus.
So
Oh,
then you get,
never mind.
you get 1, yeah.
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 So this by itself does not satisfy the initial conditions, so what do I need to do?
Yeah, do you have to do it the other way then?
I have to have
No.
a constant.
You just add constant integration.
Okay.
So I'll go ahead and add 2/9. And now it satisfies.
How can you just like,
Because I integrated. You have a
never
plus.
mind.
Yeah.
Okay.
Okay. So v prime of 0 is 0. Okay. And then what? I integrate again. So now what I'm going to get?
So the negative sinh, which gives you a positive coefficient.
Caution sinh don't switch signs like sine and cosine do.
So that's,
That
okay.
I knew.
Yeah. So minus 2/9 sinh x plus what?
2 9 6.
2/9 x. Okay, now normally you have a constant integration, but does this satisfy the initial condition? Yeah, so you don't have to add anything more. So, okay, so that part is taken care of. Okay, now, okay, so then for the W, we have our solution formula using this initial data. So we have W of xt is equal to 1/2 x plus 3t plus x minus 3t, but then those terms are going to cancel out. And then we're going to have plus 1/6, because it's 1 over 2c, but c is 3 in this case. Integral from x minus 3t to x plus 3t of sine. Okay. Okay. Now, what's interesting here is, oh, shoot. Okay. Now, all of this part works out fine. It simplifies. So it's x plus x, so we could just get x. And then we integrate this, and we get sine, so it's minus cosine of x plus 3t plus cosine of x minus 3t. We close that off. Now, okay. Something's amiss here because I'm not getting the exact same solution as before. Like, because ideally what you should do is just add this on to that and have your overall solution. So that checks out, and that checks out, but this term does not. Okay, because so there's, and actually, great. Apparently I'm destined to mess up every single class. And I'm running out of time too, but I still have some time. Hold on. Okay. Because V still doesn't depend on T. So you're going to have just, so VTT is still going to be 0. And VXX is still going to satisfy minus 2/9 sinh x. And as for the initial conditions, okay. I see no problem. Okay. The problem here is that and maybe this is why it's not such a good idea. It's perfectly fine if the right side depends only on t, like it did over there, because the initial conditions are on t, not x.
So you can't do it this way for this problem?
I feel like what I worked on paper was just fine. Okay, because what happens is I start with this. Okay, and then when I go ahead and, all right, I think a way I can get it to work out is when I integrate, remember v is a function of two variables, x and t. So I'm going to drop this assumption. V depends on both x and t, but it still satisfies this PDE. I integrate one time, and I get this. But what do I add on if it's v is a function of two variables, but I integrate it in respect to x?
Some function of t.
Some function of t. So I'll go ahead and fill that in. Let's call that psi of t. Okay. Now, I'm not going to determine it yet. I don't know what I need. Now, I integrate again in respect to x. I get this. What do I get over here?
Psi prime of t.
Um,
Oh, well,
times,
times x.
yeah. Okay. Oh, and then what else can I?
Psi of t times x.
What else can I add on?
Another function of t.
Yeah. So this is the most general form that I can have. So what happens is I take, except now, yeah. So now I have a, the trouble is now I have a t dependence. And I don't really want that. Because that certainly is going to, that's certainly going to complicate matters. Because now, if I look at, okay, so if I take Vx, I get this. Vxx is okay, so this is still satisfied. Now, let's look at Vt though. Vt is going to be, well, that goes away, and I have psi prime of t times x plus phi prime of t, and Vtt is psi double prime of t times x plus phi double prime of t. But the trouble is, this is not going to work. I need this to be, I need this to be 0 for any of this to work. Okay, so
So then you know x equals negative, phi double prime of t over.
yeah, the
psi
thing
double.
is, there's no way this can be satisfied for all t and all x, because they're two independent variables. So, okay, it's a good thing that we went through this exercise, so now we know. Don't do this unless the right side depends only on t, because at least you can make sure that the initial conditions are always satisfied. Okay, so I apologize for wasting your time yet again.
So then how do we do it?
Yes, well, that's
We
what.
did it last Wednesday
Yeah, you have to use a solution
on the
formula.
exact same equation.
I know. I just want to make sure that I have 8 minutes. So, to help you with efficiency, please hold all questions.
And it didn't take that much.
Sorry.
Okay.
I actually wrote less for that form on Wednesday than I
Sorry, I
did
thought
for
that was
this
really
one.
funny.
Okay. Okay. And then x ut of x0 is sine x. Now the homogeneous part, that was worked out just a second ago on the previous board. So it simplifies to x plus 1/6 minus cosine x plus 3t plus cosine x minus 3t. By using trig identities, you can expand cosine of the sum and the difference identity for cosine over here and get this to simplify to 1/3 sine x sine 3t using sum to product formulas. I will not elaborate further on that. So either know or be able to look up your trig identities.
Google.
What?
I said Google.
Yes. And there's a nice list in Wikipedia, in fact. Okay, plus the integral over the characteristic triangle. So 1/2c, integral from 0 to t, integral from x minus 3, t minus tau, to x plus 3, t minus tau of your right-hand side. 2 cinch squiggly d tau. Okay, so the 2's will cancel out, and the integral of sinh is cosh, so I'm only going to focus on this part, I'm not going to touch that. So integral from 0 to t, so the inner integral is, integral of sinh is cosh, so we have cosh x plus 3 t minus tau minus cosh x minus 3 t minus tau d tau. And then when you integrate cosh, it's with respect to tau now. So what you get is 1/3, and then you have, because of the minus 3 tau, and you're integrating with respect to tau, but introduces a factor of minus 1/3 sinh x plus 3 t minus tau. And then over here, you have minus, and then you have plus 3 tau. So you have minus 1/3 sinh x minus 3 t minus tau. And you plug in the limits, tau equals 0, tau equals t, because you just integrated with respect to tau. So that's where you have to plug in everything. And you get, well, I have 1/3 throughout, so I'm just going to pull that out. And that gives me a 1/9. So when you plug in tau equals t, you get minus sinh x. And then when you plug in tau equals t over here, this goes away, and you get another minus sinh x. And then when you plug in a lower limit, tau equals 0, you're going to get
Minus sinh x plus 3t.
plus, sinh x plus 3t. And then minus, but it's a lower limit, so minus and minus gives you a plus. Sinh x minus 3t. So then when you simplify as much as you can, you get, well, these two terms combined, so you get minus 2/9 sinh x. And then there are similar identities for hyperbolic trig functions as there are for regular trig functions, like sum to product formulas that can be worked out. And in the final I'll give you 1 minute to switch class. 2 minutes that I have. Here's how you can, if you don't know it. So sinh a plus b plus sinh a minus b, best done if you look at the exponential form. Okay. And what you can do is, for instance, I have like e to the a plus b plus e to the a minus b minus e to the minus a minus b minus e to the a. Okay, actually that's either minus a plus b. Okay. So for instance, I can have, out of the first two terms, I factor in e to the a. And then out of the second two terms, I factor out an e to the minus a. And e to the b plus e to the minus b, what is that? How does that simplify?
One. No, not. Never mind. This they're not being multiplied.
2 cosh.
Cosh, because of a plus.
Well, and because of the half, it gives you a cosh.
Yeah, so there's 2 cosh b. This is also 2 cosh b. So that factors out, and you have e to the a minus e to the minus a. So the whole thing simplifies to sinh a cosh B, so this whole thing, so I'll just write at the last line, that's it, plus 2/9 sinh x cosh 3t. Okay. So that is it. So this plus that, simplified to that, is the whole dang solution. But it's all in a note. So, but we'll make sure I actually talked about where each step came from, and I ended exactly on time, so yeah. Okay, and Dr. Get Dane can wait.
Why
I
do you
say.
guys have to start?
Don't even
So
ask.
we can get out of class the Monday after spring break. I don't know.
He's not in there anyway.
Huh?